Hello and good morning to everyone. So today we will be solving our questions of weekly contest 489. So in this we have four different questions. So we'll be solving each one by one. So let's see the question number one. So question number one is toggle light bulbs. So in this question we are given 100 bulbs, right? Between 1 to 100, and yeah, we are given an array bulbs in which bulbs of I will denote. So suppose we are given any number as bulbs of I. So what we have to do is, so suppose if bulbs of I is currently off, then we'll be switching it on, and if it is currently on, then we'll be switching it off, right? So if it is off, then turn it on. So suppose here initially bulbs of 10, so 10 is currently off, so we'll do it on, then 30 off to on, 20 on, then again 10. So currently 10 is on, so what we'll do is we'll make it off, right? So and at the end we have to return all the bulbs that are on. We have to return all the bulbs that are on and in ascending order, right? So see, 30 and 20 are the bulbs that are on, so we'll be returning 20 comma 30. Now similarly see the second example. So here first 100 it is off, so we'll turn it on, then again on to off. So now no bulb is in on state, so we'll return an empty array. So let's see the constraints for this question. So the bulb's length can be up to 100, means only 100 bulbs are there, and bulbs of I can be up to 100, means 1 to 100. The numbering of bulbs is from 1 to 100. So our approach is directly simulate whatever asked in the question. So let's see the code for this, right? So what we do is, as we know our bulbs is from 1 to 100, so we will make an array state from of size 101, and initially all are initially false. False means all are off, right? Then what we do is we will iterate over the bulbs array, right? And take the number of the bulb that is given. So suppose we are given 10th bulb, so what we do is we will just convert the state from false to true or true to false, just negate the state, right? And once we do this for all the bulbs given to us, then we'll see which bulbs are currently on, that is for which bulbs the value is true. So we'll iterate over the state array and check if state of I is true, then we'll be pushing that result in our result vector, and at the end we will be returning our result vector. So this way we'll get our answer. So what is the time complexity? So if you'll see, this will work for big of n time, or we can say big of 100 time, and this will also big of n time. So the time complexity is big of n. So this is a simple question. So let's see the second question. So in second question what we are asked is, we have to find the first element with unique frequency. Okay, so we are given an integer array nums, where what we have to return is, we have to return an integer denoting the first element scanning from left to right. We have to scan from left to right in nums, and whose frequency is unique. What does unique frequency means? So let's see this example. So here 20 has frequency 1, 10 has frequency 1, and 30 has frequency 2. So see, 20 also has frequency 1 and 10 also has frequency 1. So this frequency is not unique because two different elements has that frequency. But the frequency 2 is repeated only one time, and that is 30 has. So we will be returning our answer as 30. So we have to return the first element from left whose frequency is unique, right? So let's see the next example and the constraints. So here we are given 10, 10, 20, 20. The frequency of 10 is 2 and frequency of 20 is also 2. So none of the frequency is unique. So in that case we will be returning -1. So if we'll see the nums length can be up to 10 to the power 5. So what are the approaches we can use? We can either use O of n or O of n log n, right? So let's see the approach what we will be doing. So what we will do is, first of all, we will be iterating over the nums array and count frequency of each number. Frequency of each number, right? We will be counting frequency of each number. After that, what we do is count using these frequencies. We will be counting how many numbers have each frequency. So suppose 10 have frequency 1, 20 also have frequency 1. So how many times the frequency 1 is coming? So we will store 1 is coming 2 times. So after that we will be counting that, like how many numbers have that particular frequency, right? And what we want those frequencies whose count is 1. We want those frequencies whose count is 1. Then what we do is, when we will be picking the first number whose frequency occurs exactly once. Uh, so let's see the code. So what we do is, we have initially taken unordered map of integer type frequency. So in this we'll be storing frequency of each number. Then we are iterating over the nums. We are iterating over nums, and then increasing frequency of each element in this vector, right? After that, what we do is, we will iterate we will iterate over this map and count how many times that frequency is repeating. Count how many times that frequency is repeating, and store that count in another map, right? So let's see an example. 10, 10, 20, 15, 15, right? So count frequency of 10 is 2, 20 is 1, and 15 is 2. Now what we do is, we will count how many times 1 is repeating. So 1 is coming 1 time, 2 is coming 2 time. Now we will iterate over this array. So we go to 10, we check frequency of 10 is 2. We get frequency of 10 is 2. Now we check 2 is coming 2 times, so it is not unique. Again 10, frequency of 10 is 2, and 2 is coming 2 times, so not unique. Then we go to 20, frequency of 20 is 1. Then we check count of 1, so count of 1 is 1, so we get our unique element. So we return that element, and if we do not get any element, in that case we will be returning -1. So I hope you get this solution also. So let's move to the next question, that is longest almost palindromic substring. Okay, so in this question, what we are given a string which is consisting of lowercase English letters, and we have to return an integer which denotes the length of the longest almost palindromic substring in this string s. So what is almost palindromic substring? So a substring is almost palindromic if it becomes a palindrome after removing exactly one character from it. So suppose we have a substring from I to j. So if we remove any character from it and it becomes palindrome, then this substring is almost palindromic. So in that case, we have to return the length of this substring. Okay, so let's see an example. So we are given a b c a. So either we remove b. If we remove b, then we get ACA. So is it a palindrome? Yes. Or if we remove c, we get ABA. This is also a palindrome. So the length of the almost palindromic substring here is 4. Right. Let's see next example. So here we are given ZZABBA. Right. So if we'll see ZABBA. So suppose if I remove Z, then I am getting ABBA, which is a palindrome. So this substring ZABBA is a almost palindromic substring. So what is the length? Length is 5. So we return this answer 5. So if we'll see the constraints, so s dot length is 2500, right? So what are the possibilities? Big of n log n log square n, but I think n square we can't go, right? and S consists of only lowercase English letters. So we have to think of any approach in these three time complexities. So let's see our approach. So if we see any substring which is a palindrome and that has length greater than equal to 2, then if you remove one character from that, it will still be a palindrome. Let me explain you. Suppose ABBA, it is a palindrome. So if you remove any characters from the middle, either this B or this B, then it will still be a palindrome, right? Remove any one middle element, then it will still be a palindrome. Or suppose we are taken an odd length, odd length. So if we remove the middle element, then the string still be a palindrome. So case one is, so suppose a substring is palindrome and whose length is greater than equal to 2, and if you remove one character from that, it will still be a palindrome. So this is case 1. Let's see case 2. Now see this one. So this is like how to check if any substring I to j will be a palindrome after one deletion. Okay, so suppose you are given a substring from I to j and you have to check whether this is a palindrome or not. So for that, and you are allowed one deletion. So this is the second case. So case 1 is like, suppose this I and j, s of I and s of j is equal, then what we have to do is we have to check whether this substring I plus 1 to j minus 1 is like almost palindromic or not. Almost palindromic means can we make it a palindrome by removing one character. So if this substring I plus 1 to j minus 1, this substring is almost palindromic, then this bigger substring is also almost palindromic, right? This is case 1. The case 2 in this case is if s of I is not equal to s of j, means the first and last character is not equal to j. So I to j, if these two characters are not equal, then either we remove this character or we remove this character. But for this substring I to j to be almost palindromic, this inner part should be a palindrome, because in the bigger substring we can remove only one element, right? So suppose if we remove this element, then the substring from I plus 1 to j, I plus 1 to j should be an exact palindrome. Let me give you an example. C A B B A, this case. So if we remove this, then this part should be an exact palindrome to be to so that this whole string should be almost palindromic. Next case is like A B B A C. So for this to be almost palindromic, if we remove this character, then this part should be almost exact palindrome, right? So we have seen three different cases. One is exact, if the substring is exact palindrome and we remove one character, then it will be palindrome also only. Other case is the substring is not exact palindrome, but the substring I to j has I and j like same characters on the opposite side. Let's see A B C. Oh no, not this example. This case, like if s of I is equal to s of j. Let's take another example. A B C uh, B C D B A. Right, this example. So these are same. S of I is equal to S of j. Then we have to check whether can we make this as palindrome by removing one character. So suppose if I remove C, then BDB is a palindrome. So if BDB is an almost palindrome, then this whole string will be almost palindrome. So this is case one of this part. And then we have checked these two cases. So if you have noticed, we are dependent on our previous answers for our current answer. So for finding our current answer, we are dependent on our previous answer. So it is pointing towards DP. So how we will be implementing DP here? So what we do is we will make two different DPs, right? One is two DPs, one is DP of 0. So DP of 0 is will be storing all those palindromes that are exact palindromes. So DP of 0 I comma j will tell us whether substring I to j is exact palindrome or not. Exact palindrome, right? And the other one is DP of 1, which will tell us that DP of I to j means substring I to j is palindrome after one deletion or not, right? So we'll be using these two DPs, and also we will be using DP of 0 to calculate DP of 1. If you remember, we have discussed that CABBA. Suppose this is a substring from I to j and C is not equal to A, then we have to either remove C or A. So if we remove C, this ABBA should be a palindrome. So how we will be checking this? Using DP of 0. Using DP0, right? Using DP0, we will be checking whether this part is palindrome or not. If this part is palindrome, we can directly remove the C. So we will be using DP0 to calculate DP1. And also, as we know, all one length substrings are palindromes, and length 2 substring I to j is palindrome if both characters are equal, that is s of I is equal to s of j, and for length equal to greater than 2, it will be palindrome if s of I is equal to s of j. Suppose we have a string I to j and s of I equal to s of j, so it will be palindrome if s of I equal to sj and this substring that is from I plus 1 to j minus 1 will be a palindrome, right? If this will be a palindrome and these two outer characters are equal, then this whole string will be also a palindrome. So length 2 is palindrome if f of I equal to s of j, and dp of 0 from I plus 1 to j minus 1 is also a palindrome. So what we'll do is we'll do iterations depending on the length of the substrings. As we can see here, this bigger substring depends on this smaller substring for checking whether this substring is palindrome. The answer depends on this. So we'll be doing iteration depending on the length, right? So if you'll see the code, so what we do, we have made two DPs, DP0 and DP1. DP0 to store all the substrings to check whether they are exact palindromes, and this is after one deletion, right? And then what we do is we have made all the length 1 substrings as palindromes. As we know, all length 1 substrings are palindromes only. Then we are iterating over the length from length 2 to n. So length 2 to n, we are checking all the lengths, right? And we have I and j to mark the substring from I to j, right? So we first check whether it is an exact palindrome or not. So if s of I equal to s of j, if s of I equal to s of j, and let's say length is 2, a, if both are equal, then it will be a palindrome. We will mark it 1. If length is greater than 2, then for this to be palindrome, this substring that is from I plus 1 to j minus 1 to be a palindrome, that is dp of 0 I plus 1 to j minus 1. So we are storing this answer in this, right? This is for exact palindrome. So once we check this exact palindrome, then what we do is we will be checking whether we can make it palindrome after one deletion or not. So we have made a character OK equal to 0. So here we have three cases in this not exact match, right? We have three cases, that is the outer matches I and J matches. So if I and J matches, then this inner part should be almost palindrome. For this whole string to be almost palindrome, let's see an example. A, B, C, D, B. Suppose this is our string. So for this whole string to be almost palindrome, and these are the cases like S of I is equal to S of J, then we check the inner string. if the inner string is almost palindrome. Is it almost palindrome? Yes, we can. If we remove C, BDB is almost palindrome. So how we check whether this inner string is almost palindrome? We can check using DP1, because DP1 store the answer. So DP1 of I plus 1 and j minus 1 will tell us whether the inner string is almost palindrome or not, right? What is other case? If this s of I is not equal to s of j, if s of I is not equal to s of j, let's take an example, a b c c b. So s of I is not equal to s of j, then we check whether this dp of I plus 1 to j, is this a complete palindrome or exact palindrome, right? See, dp of 0, we are using dp of 0. If this is exact palindrome, then if we remove this character, then this whole string is substring is almost palindrome, right? We mark it exact palindrome. Let's take another example, b c c b and a, like this last character. So if s of I is not equal to s of j, but this I to j minus 1 is exact palindrome, then this whole string is almost palindrome. So we mark dp of I comma j as okay, and then we'll find the best length, the current length. If see here the length is 5, and suppose we have stored already some best answer, so we'll take that answer, and at the end we'll return this answer. So next is question 4. So our next question is 3845, which is maximum subarray XOR with bounded range. So what is given here? So we are given a array of non-negative integers, right? And an integer k. So we have to select a subarray of nums such that the difference between the maximum and minimum, that is a, suppose we have get a subarray from I to j. So maximum of I to j minus minimum of I to j should be less than equal to k, is at most k, means that value should be less than equal to k, and the value of the subarray, so value of this subarray is the XOR of all the elements in the subarray. XOR of all the elements from I to j is the value of this subarray, and we have to return an integer which denotes the maximum possible value of the selected subarray. So this is a hard question and it is a very good question. I like this question. So let's see some examples. So we are given an array 5, 4, 5, 6 and k is equal to 6. So if we'll see the subarray 4, 5, 6, so 6 minus 4, 6 minus 4 is less than equal to 2. And if we'll see the XOR of this 4, 5, 6, it's 7. So we have returned our answer as 7. So this is a maximum XOR that we can get. Next example is 5, 4, 5, 6 and k is equal to 1. So if we'll see 6 minus 6, 6 minus 6 is 0, that is less than equal to k, and so the maximum XOR that we can get is 6 only. So this is the value. Next we see the constraints. So if you see the array length can be 4 into 10 ki power 4. That means either big of n or n log n solution we have to think of. And nums of I can be up to 2 ki power 15, right? So remember this 2 ki power 15, because we will be using it further in our approach. So let's see the approach. So first what we do is we have to find a valid subarray whose difference of maximum and minimum is less than equal to k. So to find the valid subarray, what we'll do is we'll be using sliding window, right? So what we do is we'll add an element at index r to this window, and then check if the window is valid, then nothing, we'll do some operations that we'll discuss later. If window is invalid, means the difference of max minus min is greater than k, then what we do is we'll be shrinking the window until it becomes valid again, right? So we'll be finding the valid subarray using sliding window. Okay, now suppose we get a subarray that L to R, which is subarray from index L to index R, which is valid. That means maximum from L to R minus minimum is less than equal to K. But the thing is that how we'll be finding the maximum and minimum of the window? How will be finding the maximum and minimum of the window? And we are also updating the window. So these maximum and minimum should keep updating as we update the window. So what we are doing for that is we are using two DQs, one DQ for minimum and one DQ for maximum. The minimum one will store the elements in increasing order and the maximum will store the increasing in elements in decreasing order. So let's see how this DQ will work. So I have taken an array nums 5 3 4 and initially our minimum DQ and maximum Q both are empty. So at index 0 our value is 5. So minimum is empty, so we'll directly push the index. So in this queues we won't be storing the elements, we will be storing the indices, right? So we'll push 0. So M1 now has index 0 whose value is 5. Then maximum DQ. So this is also empty, so we'll be pushing 0. So this maximum is 0. So now minimum is 5, maximum is 5. Both has index 0 only, right? Now suppose we have added element R is equal to 1 to the window. So if you'll see the value is 3. Value is 3. So now first we see the increasing or the minimum DQ. So already we have index 0 whose value is 5. But if you'll check 5 is greater than or equal to 3. This 5 is greater than or equal to our current element 3. So what we'll do is we'll pop this element, right? We'll pop this element and now we'll be pushing our new element that is 3. So we have pushed index 1 whose value is 3. Why we have removed this current element? Because it is greater than our the current element. It is greater than this 3. So we have removed 5. Now what we do is we update the maximum also. So so in maximum we have 5 and our current element is 3 and 5 is 5 less than equal to 3? No. So we won't be pop this 5. We directly push this 3 with 5, right? Because we want the elements to be decreasing order. So our max gets updated to 0 and 1. So if you'll see our min has nums of 1. Our minimum is 3 and maximum is 5. Now if you'll see at index r is equal to 2. At index r is equal to 2, we have the value as 4. And the minimum in min we have only index 1 whose value is 3. So if we see is 4 lesser than 3, is 4 lesser than 3? No. Then we directly push 4 ahead of 3 instead of popping 3. So now our min has become 1 and 2 and the values has become 3 and 4. Next is we have max. So in max what we have? We have index uh, we have values 5 and 3, right? Now we'll see 4. So we will see 3. 3 is lesser than 4. So what we do is we'll pop it and then we'll compare 5 and 4. Is 5 lesser than 4? No. Then we directly push 4 here. So this way we'll be finding our min and max using this two DQs, one to store the minimum elements and one to store the maximum elements. Okay, next what we do is we find the minimum and the maximum of the window. What else we need? We need the XOR of the window also, right? So if sorry, if we iterate over the whole array to find the XOR, that will increase our time complexity to big of n square. So what we can do is we can use prefix XOR. So what is prefix XOR? So let's say we have px of I, that is prefix at index I. It will give us the XOR of all numbers from 0 to I minus 1. That is we'll store 0 to XOR of all numbers from 0 to I minus 1 at px of I, and then p XOR of all numbers up to I plus 1 is equal to the XOR that we have stored at I and nums of I, right? So if you have to find XOR of the subarray L to R, what we do is we'll take XOR of all the numbers from 0 to r as XOR of r plus 1, and then do XOR with these numbers. So we get XOR of L to r, because these numbers are repeated twice. So a XOR a is equal to 0. So as these are repeated twice, their value become 0. So we get XOR from L to r. So now we get minimum and maximum of the subarray. We get the minimum and maximum of the subarray, and also we get the XOR of the ranges, right? So now for a fixed r, suppose we have a valid subarray from L to R. We have valid subarray. So all the subarrays from L to R or L plus 1 to R, like this, all these subarrays are will be valid, right? So we have to find a k, like this is L to R. We have to find a k, index k, such that the XOR from k to r is maximum in this range L to R. So we have to find this k now, right? Or we can see this like maximum, this will give us the XOR of k to r. So we have to maximize this k, and where k belongs to, that's current range L to R of the subarray. So if we'll check each possibility of k, like if we'll take k as L, then L plus 1, L plus 2 up to R, then the time complexity will be big of n square. So how to optimize this one? So what we can do is, as we have already noticed, our nums of I is up to 2 ki power 15, right? And if we represent it in bits, we will get only 15 bits, right? So if we and we have already computed the prefixes. We have already computed the prefixes and stored the bits of. So if we store the bits of all the prefix of L to R, in a trie. I hope you all know what is a trie. So where every node in a trie has two children, 0 and 1. Either it is 0 bit or 1 bit, right? Now suppose we stored all the prefixes from L to R in a trie. Then what we want? We want to maximize prefix of R plus 1, XOR prefix of K. That is the XOR from K to R plus 1. We want to maximize this. And we already know what is the prefix of R plus 1. We just have to find the prefix of K. We have prefix of R plus 1 and we have to find the prefix of K, right? So what we will do is, what we'll be starting find greedily. So we take prefix of r plus 1 and then start from most significant bit to less significant bit. Please keep waiting, I'll explain you with an example so you will be getting it more properly. Just let me complete it. So if prefix of r plus 1 bit is 0, as you know, 0 XOR 1 is 1, 1 XOR 0 is also 1, but 0 XOR 0 is 0, 1 XOR 1 is 0. So if prefix of r plus 1 bit is 0, what we try to find is, we try to find 1 to maximize our answer. And if its bit is 1, we try to find 0 to maximize. And suppose if we don't get, suppose prefix of r plus 1 bit is 0 and we try to find 1, but 1 is not there, then we'll be moving on with 0 only, because one child is there. So let's take an example to explain this more clearly. So suppose prefix of r plus 1 is this value 0 1 0 1 0, and we have stored these prefixes in the trie. Now if you see the most significant bit, the most significant bit is 0. So what we want for this to be in prefix of k, we want that this bit should be 1. So does this has the bit 1? No, remove it. Yeah, these two has this bit as 1. Okay, so our answer will be 1 amongst these two. Then next bit is 1. Next bit is 1. So for 1, what we want? We want to find 0. So this has 0, but this does not have 0. So this will also be removed. So we'll be taking this 1 0 1 1 0. So the XOR of 0 1 0 1 0 XOR 10110 will be maximum out of these three XORs. So we'll be taking this value, right? So that's why. So for finding the our XOR greedily, we are using trie. So let me explain you what is a trie. So let's take three examples: 00101, 10110. So initially, zero will be storing this. So 0, then 0 will be pointing to this child. Again 0, it will be 1 will pointing to this child. Then 0 will be pointing like this way. So if you'll see here 0 pointer, so we'll take 0. Here also 0 pointer, 0. Here pointer is 1. Here the pointer is from 0, so 0. Here the pointer is no pointer. Suppose no pointer means we get 0010. So this way we'll be storing all the prefixes, of the range L to R, and then using the prefix of R plus 1, we try to find the best one that will maximize our answer. So if you'll see our complete approach, if you'll see our complete approach, so what we are doing is, for each index R, we expand the window and add nums of R. And if the window is invalid, means while min minus max is greater than k, we will shrink the window. We will shrink the window, remove prefix p x of L from the trie, and move L forward by 1. Suppose now we get a valid window from L to R. Then what we do is, we will query trie with px of R plus 1. That is, we want to find a k such that XOR of px of R1 and XOR of px of k is maximized, where this k belongs to L to R. And we also insert this px of R plus 1 into the trie for future uses, right? So I hope the approach is clear to you. Now let's see the code part. So first of all, we are making a our struct for trie. So we have made a node, and each node has two children, 0 and 1, and also count two. Okay, so child of 0 is equal to child of 1. Initially both are -1 and count is 0. So first function is insert function. So in insert function, our current is equal to 0. Wait, I'm tired a bit. If, like, current node, array yaar, like this current node is equal to 0. If current dot count, we increase current dot count to 1, right? And then we will take the prefix. Suppose 00101, we take the prefix and then take the most significant value. So the most significant value is 0, so we'll put 0 here. Then next value, then again create a new node and then push 0, and then again take this node and then push 1, again take this, so 0 will push this. So this way will be insert all the nodes. Now suppose we get a new node as 01001, so which again count is 0, so we check whether 0 is created. Yes, 0 is created, so we'll go here. Next is 1. Is 1 has any child? No, so we'll create node 1, then again node 0, and so on. So this way we'll be inserting in the trie. Now suppose we have to erase, so our current is 0. So what, for erasing, what we do is, we are removing one prefix, so we decrease the count by 1, and we again keep calculating these bits, right? So suppose we have to remove this 0, so this 0 is here, so we reduce the count by 1, and then we go to 1 here. So if now this 1 has count as 1, so if we remove this, the count has become 0. So if the count has become 0, then we directly disable all the childs of this one. Okay, so for a node, for any node, if the count becomes 0, we directly disable all the nodes of that, all the children nodes of that particular node, right? And then this is the maxjor function. This function is also part of the our struct. This function is maxjor. So in maxjor function, what we are trying to find is, for any particular x, we are trying to find which is the best, which is the best possible zor we can get, right? So suppose x is 1 0 1 1 0. So for 1 we'll try to find 0 if any 0 is possible. For 0 we try to find 1 if any 1 is possible. For any 1 we try to find if 0 is possible. So this max jor will helping us to find the best prefix that is stored in the trie, right? So this is our struct. Now this is our main function that is given to us. So in this main function we are given the array and then k. So first of all we have stored all the prefix jors, right? And then we have made two dqs, min and max, for finding the minimum and maximum in optimized time. Then we have declared a trie, and l is equal to 0 and answer is equal to 0. L is the pointer, and then we have inserted the first prefix px of 0, that is equal to 0 in our trie. And then increased our we have started expanding our window and checking if min is empty, min is not empty. And so we are with this loop we are maintaining our minimum dq, we are updating our minimum dq. And with the second loop we are maintaining our maximum dq, that is inserting the element or popping back depending on the element in the minimum and maximum dq. Okay, and this loop is for shrinking if the window is invalid. Suppose if the window is invalid, then we have to shrink. So this loop is handling that case. And now suppose after shrinking we get a valid window from L to R. So we called our maximum zor function of the trie, and we have passed the prefix of prefix of all the numbers up to from 0 to R, right? And then once we get our maximum zor, what we do is we insert this zor also in the trie, and at the end we will be returning our answer. So I hope I am able to explain you all the 4 questions properly with proper approaches and uh, correct codes. So if you like the video solution, please make sure to like, share and subscribe the channel. Thank you.